chapter 7.4, integration by partial fractions. And I'm going to show you the conventional way for doing it, and I'm also going to show you a little trick called the Heaviside cover-up method. It's a little trick. All right, the one thing I want to mention just before we start off on integration with partial fractions is that there are rules for differentiation, but only techniques of integration. So the rules for differentiation might be that you have the sum difference rule, you have the product rule, the chain rule, and the techniques of integration you've learned mainly use substitution. Have you learned integration by parts yet? Integrate? They got integration by parts. So I think of use substitution as kind of reverse chain rule. This is kind of, the books won't say that word, but that's why I think of reverse chain rule. Okay, integration by parts is kind of the reverse product rule. So what's the point I'm trying to make here is that differentiation you have rules for. You can look at something and say, okay, I'm going to apply the product rule, I'm going to apply the chain rule, I'm going to apply some combination of different rules. But integration is basically guessing. So integration is basically guessing. Guess the function or expression whose derivative is what you want to integrate. Okay? So you're trying to guess something whose derivative is the thing you want to integrate. Now there could be integrals that look very similar that have very different answers. Okay? Let's do a few practice ones here. If I do the integral of 2x, let's say x squared minus 1 to the 100th power dx, or do the integral of 2x over x squared minus 1. Okay, or do the integral of 1 over x squared plus 1, and we'll do the integral of 1 over x squared minus 1 dx. Right? So the first one here, the integral of 2x times x squared minus 1 to the 100th power dx. This is actually the result of a chain rule. This was the result of a chain rule. Sometimes if you do enough integrals, you can look at the integral and then kind of do it in your head. But if you don't have enough practice doing it, you can use a technique called use substitution. So in this case, what would I set u be equal to? What would I set u be equal to in order to do this integral? Yes, sir. Yeah, x squared minus 1, x squared minus 1. So that means that du is equal to what? Du is equal to 2x dx. So I could rewrite this integral now. I could rewrite this integral as u to the 100 du. U to the 100 du. And what's the integral of u to the 100 du? So what would the integral of u to the 100 du be? It would be, anyone want? Yes, ma'am. Good. Yeah, right. So it's going to be 1 over 101 u to the 101. Right, plus c. Very good. Excellent. All right. How about if we did the integral of 2x over x squared minus 1 dx? The integral of 2x over x squared minus 1. what would I set u be equal to here, do you suppose? U is equal to, anyone? Yes, very good, x squared minus 1. So that means that du is equal to what? 2x dx, right? 2x dx. So this integral now is du over u. Du over u. Okay, integral of du. And what is the integral of du over u? Do you remember? So this one turns out to be some special function here. So what's the integral of 1 over x? Dx is the natural log of absolute value of x plus c. So this is the natural log of u, absolute value of u, plus c. So this is equal to the natural log of x squared minus 1 plus c. Okay. Now you can always check to see if you did an integral correctly, because you can differentiate the answer and see if you get the integral. You get the integrand, that is. So if I differentiate natural log of x squared minus 1, I get 1 over x squared minus 1 times the derivative of x squared minus 1, which is 2x. So I see that the derivative of natural log of absolute value of x squared minus 1 plus c is equal to 2x over x squared minus 1. Now remember, the derivative of a constant is 0. So that's why I have this constant of integration. So I can say that the integral is natural log of, I can differentiate any number of this form, natural log of absolute value x squared minus 1, I could say plus 100, plus pi, plus e, plus a million. The derivative of that expression would be 2x over x squared minus 1. How about the integral of just plain old 1 over x squared plus 1? So what's the integral of 1 over x squared plus 1? So this is one that you have to kind of remember. I could go through the derivations a little bit more involved, but this one turns out to be, does anyone want to venture a guess? Do you remember? It doesn't involve natural log, it involves another type of function, a trig type function. What do you call guys that go to the beach? Tangents. Tangents, so it involves the tangent function here. So this is the arc tangent, this is arc tangent of x. So the integral of 1 over x squared plus 1 is equal to arctan x plus c. Okay, now let's do let's do the partial fractions one. Let's do partial fractions. I'm going to show you the way to do it the long way, and then I'm going to show you the shortcut. All right, so I got the integral of 1 over x squared minus 1 dx. That's equal to the integral of 1 over x minus 1 times x plus 1 dx. I'm going to take this 1 over x minus 1 times x plus 1 and express it as a times x minus 1 plus b times x plus 1. Okay? So now it's algebra. I'm going to write that as a times x plus 1 plus b times x minus 1 all over x minus 1 times x plus 1. All right? Okay, and so this is equal to ax plus a plus bx minus b all over x minus 1 times x plus 1, and that's equal to a plus b times x plus a minus b all over x minus 1, x plus 1. Okay, now this is equal to 0x plus 1 all over x minus 1 times x plus 1. So that tells me that a plus b is equal to what? If 0x equals to quantity a plus bx, so a plus b is equal to 0, right? A plus b equals 0. What's a minus b? A minus b is equal to 1. Yeah, very good. Now I have to solve these two equations and two unknowns. So I get 2a is equal to 1, which means that a is equal to a half. And I get, if a is equal to half, that means b must be equal to a plus b is 0, so b must be negative a half. Okay, once I know that, I got the integral of 1 over x squared minus 1 dx is equal to 1/2 x minus 1 dx plus the integral of negative 1/2 x plus 1 dx. So that's equal to 1/2 integral of 1 over x minus 1 dx minus 1/2 integral of 1 over x plus 1 dx. And so now this is equal to 1/2 natural log of absolute value of x minus 1 minus 1/2 natural log of x plus 1 plus c. So the reason we call this the method of partial fractions, is because I take a rational expression like 1 over x squared minus 1 and I express it as the sum of two fractions here. Now I'm going to show you the trick. Okay? So I got 1 over x minus 1 times x plus 1 is equal to a over x minus 1 plus b over x plus 1. Okay. So I'm going to multiply both sides by x minus 1. All right? So I'm going to multiply both sides by x minus 1. I'm going to multiply both sides by x minus 1. All right? Now, when I do that, I'm going to do the cover-up method. I'm going to cover up the x minus 1. I'm going to cover up the x minus 1, and I end up here with x minus 1. Okay? So I'm going to cover this up over here. All right? Now I'm going to say, now I'm going to cleverly set x is equal to 1. Okay? So I'm going to cover up the x minus 1, cover up the x minus 1. When I set x is equal to 1, this goes away because this is 0. I end up with a, and when I put in 1 for x, what do I get here? On the left-hand side, if I put 1 for x. If I plug in 1 for x, I get what? 1 over 2, right. So I get a is equal to, this leads to a is equal to 1/2. So I didn't have to solve equations and unknowns. I multiply both sides by x minus 1. I cover this up, and I have an x minus 1 over here. I cleverly set x equal 1. This goes away. I get a is equal to 1/2. Okay, let's do b. B, I'm going to multiply both sides by x plus 1. Multiply both sides by x plus 1. Okay? So multiply both sides by x plus 1. I get this. I get b, just plain old b here. And I got a x plus 1 over here. So I got... Now, I'm going to cleverly set x equal to what? Cleverly set x is equal to... So what? When I multiply both sides by x plus 1, I want this to go away, so I set x equal to what? Negative 1, right. So cleverly set x equal to negative 1. Very good. When I cleverly set x is equal to negative 1, because I covered up the x plus 1, this one goes away, so I get b is equal to, if I plug in negative 1 for x, what do I get here? If I plug in negative 1, I get, for x, I get So I plug in -1 for x, I get -1/2, right? So I get b is equal to -1/2. Okay, good. That's called the Heaviside cover-up method. Okay, I'm going to do a more difficult problem. For you. All right. So I'm just going to make it up off the top of my head. I'm going to make up the problem off the top of my head. All right. So I'm going to do integral of 2x squared minus x plus 4 all over x minus 1, x plus 1, and x minus 2 dx. Okay, I just made it up. And in fact, I'm going to make it even more complicated. I'm going to multiply this out so that I'm going to rewrite that in. So that's x squared minus 1, x minus 2. So that's 2 minus 2x squared minus x cubed. So I get x cubed minus 2x squared minus x plus 2. Okay, so if my integral was 2x squared minus x plus 4 over x cubed minus 2x squared minus x plus 2 dx. All right, let's suppose someone gave you this problem. Now you would be befuddled because you're like, how am I going to guess something whose derivative is this thing? So the chances of you guessing the answer is very small, just, negligible that you can guess. So what I'm going to do is I'm going to factor this as, so then I get 2x squared minus x plus 4 over x minus 1, x plus 1, x minus 2. That's equal to a over x minus 1 plus b over x plus 1 plus c over x minus 2. Okay, so I got 2x squared minus x plus 4 all over x minus 1, x plus 1, and x minus 2. Okay. So I got a over x minus 1 plus b over x plus 1 plus c over x minus 2. Now, there's two ways I can do this. I can do it the long way. Okay, we're going to do it the long way. If I do it the long way, I get a times x plus 1, x minus 2, plus b times x minus 1, x minus 2, plus c times x minus 1, x plus 1, all over x minus 1, x plus 1, x minus 2. Okay? That's this thing over here. Then I'm going to write a times x squared minus x minus 2 plus b times x squared minus 3x plus 2 plus c times x squared minus 1 all over x cubed minus 2x squared minus plus 2. Okay? And so this is going to be equal to a plus b plus c x squared, okay, plus negative a minus 3b x plus negative 2a plus 2b minus c, okay, all over x cubed minus 2x squared minus x plus 2. Then I have to set a plus b plus c is equal to 2. Negative a minus 3b is equal to negative 1. And negative 2a plus 2b minus c is equal to 4. And then solve. That's the long way. I have to split this up into three partial fractions, go through all this algebra and arithmetic, which I hope I did correctly, which I'm not sure because I can make careless mistakes. But here's the trick. Here's the trick method. The trick method is now I'm going to multiply both sides by x minus 1, and then set x is equal to 1. Okay? I'm going to multiply both sides by x minus 1, cover up, cover up. This is times x minus 1, this is times x minus 1. Okay? So, multiply by x minus 1, x minus 1. Now I'm going to set x equal 1. When I set x equal 1, this is 0, this is 0. I get a is equal to, I'm going to plug in 1. What do I get? 2 times 1 squared, so 2 times 1 minus 1 plus 4. So that's going to be 5. So I get a is equal to 5 over 1 plus 1 is 2. 1 minus 2 is negative 1. So this is going to be 1 plus 1 is 2 minus 1. So that's minus 2. So a is equal to negative 5 halves. All right. So let's now let's figure out b. So now I'm going to multiply both sides by x plus 1. I'm going to multiply both sides by x plus 1, and then I'm going to cleverly set x is equal to what? Negative 1. Yeah. So I'm going to then cleverly set x is equal to negative 1. Very good. So I'm going to multiply both sides by x plus 1, and I got x plus 1, x plus 1. Okay. All right. So I multiply both sides by x plus 1. I get b is equal to. Now I'm going to plug in negative 1. So negative 1 squared is 1. 2 times 1 is 2. Then a negative 1, that's plus 1. So that's 3 plus 4 is 7. So I'm going to get b is equal to 7 over. I'm going to cleverly set x is equal to negative 1. So that's negative 2. Negative 2 times negative 3. Negative 2 times negative 3 is 6. So b is equal to 7, 6. Now we're going to do c. We're going to multiply both sides by what? Multiply both sides by x minus 2, and then cleverly set x is equal to what? I multiply both sides by x minus 2, then I'm going to set x is equal to 2. Very good. Excellent. Okay, so I got a x minus 2, x minus 2. Okay, multiply both sides by x minus 2. This x minus 2 clears up, so I get c is equal to, when I set x is equal to 2, this term goes away, this term goes away. I get c is equal to, I have to plug in 2. 2 squared is 4. 4 times 2 is 8. 8 minus 2 is 6. 6 plus 4 is 10. So that's 10 over 2 minus 1 is 1. 2 plus 1 is 3. So I get c is equal to 10 thirds. C is equal to 10 thirds. Okay. Now this is the moment of truth, do these things actually make this thing true? Because I may have made so many arithmetic errors, I don't even know. You know, I did so much algebra. Does that work out? Does a plus b plus c equals 2? I don't know. Let's take a look. B plus c is 7 over 6 plus 10 over 3. So that's going to be, oh gosh, so this is going to be 20 over 6. That's 27 over 6. 27 over 6 is what? 27 over 6. I take out the 3, so that's going to be 27. 27 over 6 is the same thing as 9 over 2. 9 over 2 plus negative 5 over 2 is 4 over 2. Good, got it. See, so then I solved 3 equations and 3 unknowns pretty well. Now negative a minus 3b is negative 1, so that means a plus 3b is negative 1. A plus 3b is going to be 7 halves. 7 halves plus negative 5 halves is going to be 2 halves, so that's 1. So a plus 3b is 1. Good. So I won't bother to check the third one. So now once I figure that out, I get the integral of 2x squared minus x plus 4 over x minus 1 times x plus 1 times x minus 2 dx is equal to negative 5 halves x minus 1 plus 7/6 x plus 1 plus 10/3 x minus 2. Okay? So that's equal to, so that means that so that's going to be equal to negative 5 halves integral 1 over x minus 1 dx plus 7/6 integral of 1 over x plus 1 dx plus 10/3 integral of 1 over x minus 2 dx. So it's going to be negative 5 halves natural log of absolute value of x minus 1 plus 7/6 natural log of x plus 1 plus 10/3 natural log of x minus 2. And there's your answer. So the integral, so this integral here, if you give it this integral, it's quite a bit of work. You have to recognize that this denominator can be factored into linear terms. You can use what's called the method of partial fractions. You don't know how to integrate this, but you do know how to integrate each of these individual fractions, rational expressions here. And so that's called the method of partial fractions. Now, I oversimplified a little bit because the only conditions I considered were where the bottom terms, these bottom terms are linear terms. But it's a little bit more complicated if you had some that look like this. So if I have the same problem, but this is x squared plus 1, this is called an irreducible quadratic. So you're not able to necessarily set it up in this way. You're going to have another piece in there. You're going to have another piece in there that's called plus dx plus e over x squared plus 1. You know, you're going to have another little part over there. So you can, in the book, they're going to describe all the nuances here. But I'm just, for the purposes of today's lecture, I'm just going to give you the simple version. This is basically the thought here is I'm going to take a complicated rational expression and express it as the sum of 3 kind of basic expressions that you know how to integrate. So that concludes our little lecture today. I did the same thing with other classes. You know, we shortened the classes in the morning because it was so cold out. So that's kind of the basic deal. That's called the method of partial fractions. Method of partial fractions is I'm taking a rational expression and expressing it as partial fractions. So just